24 June 2021. A 12-story condo in Surfside, Florida collapsed, considered as one of the deadliest structural failures. Do you know why this happened? The main reason behind this was concrete deterioration caused by corrosion and chloride attack, which weakened the structure and reduced its service life. Concrete is the second most used material in the world after water, which caused the production of approximately 8% of global carbon dioxide emissions, leading to global climate change. So, where's the solution? Introducing Ecoconcrete. By adding fly ash, silica fume, and slag produced as byproducts as partial replacements for ordinary Portland cement, we can try to create stronger, more durable, and eco-friendly concrete. Here, we are analyzing two scenarios, such as the base case scenario and the alternate case scenario. In the base case scenario, only ordinary Portland cement is used in the concrete mix design. The mix consists of 425 kg of OPC, 880 kg of fine aggregate, 950 kg of crushed coarse aggregate, and 170 kg of tap water. The final concrete mixture weight is 2425 kg per meter cube.
Here, in case of transportation, we consider OPC from Lafarge Cement Bangladesh, Sylhet, fine aggregate from Chittagong, Sylhet, and coarse aggregate from Bholagans, Sylhet of Bangladesh. Our concrete mix has a 0.4 water binder ratio, with aggregates making up 75.4% of total mass, and the total volume of aggregates in BCS and ACS also kept the same. In our alternative mix, 40% of the cement is replaced with supplementary materials, while 40% is coal fly ash. The water cement ratio, mass of total binder, aggregate volume, and the fine aggregate remains unchanged. Mentioning that coal fly ash is obtained from Matabai, Chittagong. Otherwise, the source of cement and fine aggregate is same as base case scenario. Here is the total mix design for ACS.
According to our alternative concrete mix design, the potential environmental impact reduction value is 23.6%, which fulfills the minimum allowable value of 15%. So the mix design can be declared as environment friendly. The durability check used Life 365 software, where we have found the service life of our alternative case scenario is 23.67 years. Therefore, the service life score can be considered as 2.
Now, let's jump into the decision-making process. We have followed two decision-making process for the optimal service life score and EIR value. In decision-making process 1, we have conducted trials in two phases. In trial phase 1, the combination of supplementary cementitious material is made up of coal fly ash and silica fume, and in phase 2, we used coal fly ash and GGBS. According to the tools used, GGBS performs poorly in both service life and the EIR value for any material location scenario. Therefore, it might be unsuitable for the ACS mix. In contrast, increasing silica fume content improves service life and reduces the EIR value for any location scenario. In the decision-making process 2, 3 location scenarios were considered where maximum acceptable distance for supplementary cementitious materials are taken. The key difference between location scenario 1 and location scenario 2 is the transport mode. Waterway transport improves EIR value due to lower energy use. Although location scenario 3 was expected to outperform location scenario 1 based on waterway efficiency, but location scenario 1 still gave a better EIR. However, silica fume and GGBS are not available within the transport boundary set for this competition. We attempted to source silica fume from Kachpur, Narayanganj and Agartala, India. Unfortunately, the distance from this location exceeds the permissible limit set by the rulebook. Therefore, a mix design containing 60% OPC and 40% coal fly ash is considered the optimal mix design for ACS. Coal fly ash offers the best EIR value of all the tracks. To the best of our knowledge, this is the optimum combination considering the service life and EIR staying within the boundary condition from our location of CUET, Bangladesh.
Next, we shall present the importance of life cycle assessment, which plays a crucial role in evaluating the environmental impact of construction materials and process. In our assessment, the LCA showed notable reduction factors of 31.9% in global warming potential, 8.2% in carcinogenic effects, 29.5% in ozone depletion, 17.7% in ecotoxicity, and 30.6% in fossil fuel depletion. These changes are influenced by material choices, the calcination of cement being a major contributor of global warming, which results in high carbon dioxide emission during production, while sand and heavy metals of fly ash impact ecotoxicity and fossil fuel use. Using supplementary materials like fly ash helped reduce dependency on cement clinker, also lowered carbon dioxide emissions and energy consumption. Moreover, LCA helps to identify such material-related impact, which enable us to make more sustainable design decisions.
As we move toward a greener future, our Ecoconcrete innovation represents sustainability, durability, and advanced engineering. It supports SDGs like 9, 11, 12, and 13 by strengthening infrastructure, fostering sustainable cities, conserving resources, and combating climate change. Together, we are not just building structures, we are shaping a stronger and greener future.
Let's build with purpose and innovate for a better tomorrow.